I think it started.
Hi everyone, I'm Sunaina and today we'll be learning about orders and primitive roots. So I'm sure you guys know what Fermat's little theorem says. It says that if you have a prime P and you have any number A such that P doesn't divide A, then A to the power P is congruent to A mod P. Can you guys hear the background noise? No.
No, it's clear.
Okay. So this is what Fermat's little theorem says. Right. So you know what Euler's theorem, I'm sure you guys must have seen, uh, which says something almost similar. Oh, also this equivalently says that A to the power P minus 1 is congruent to A mod P. This is equivalent because A doesn't divide. Oopsie. A doesn't divide P. Sorry, P doesn't divide A.
One mod P or
It's going to be
A?
one mod P.
Yes, it's 1 mod P. My bad. Yeah, thanks. And we can generalize this essentially because like P minus 1 is essentially phi of P. So there's another theorem called the Euler's. What's the spelling of torsion? Torsion. Do not quote me there. Theorem, which says that um, if you have GCD of A comma M to be 1, then A to the power phi of M is congruent to 1 mod M. Yes. So we can see that there. So if I have two numbers A and M, then there exists a D such that A to the power D is congruent to 1 mod M. Well, how? We know that there is one candidate, which is phi of M. We know that by Euler's torsion theorem, A to the power phi of M is congruent to 1 mod M. So one such D exists. But this is sort of boring, and also it doesn't give us much information. Much information in the sense um, that D phi of M might not be the smallest, not be the smallest exponent which satisfies that condition. Which satisfies the condition. For example, I know that by Fermat's little theorem, 4 to the power 12 is congruent to 1 mod 13. But so is 4 to the power 6. So yes, we do get that phi of M satisfies that this condition, but it would be nice if I could find the smallest. It would be nice if I could find the smallest D. Or even better question, is that D unique? So this motivates something called orders. Usually we define orders modular or prime but we can do it with respective to any number. It doesn't necessarily have to be a prime. But okay, so how is order defined? Well, um, okay, order. If you're given a number, we are working with prime, so if you're given a prime p, oh, also excuse me for bad handwriting. My handwriting is way better on paper, but like here the whiteboard is bad, so I'll blame it on the whiteboard. The order of an integer. Oh wait, shit. Oh no, not shit. Um, guys, if you guys are commenting, so not commenting, uh, writing in chat, I cannot. Wait, what is same for everyone? I'm not able to see it on the chat.
It's
Can
like
somebody?
your handwriting here is 1,000 times better than everyone. See?
Oh, achha, I thought people are not able to listen to me. Oh, thank you. Yes. So if you're given an integer, but currently let's work with positive integer to make life easy. Not and then it's a. So if you're given a positive integer a and
ভালো লাগলো না তো কি করবে তাহলে কি করবে বাবা দেখো তো কি করবে
such that this I think some disturbance such that p doesn't divide a, then there exists d, which is the smallest positive integer such that a to the power d is congruent to 1 mod n. This and d is called order of a mod.
What's M? Shouldn't it be P?
Oh, it could be p. My bad. Thank you. Modular p. Some people also write order of like this notation. So yeah, I'll be using both of them interchangeably. So yes. Okay, I think we should if uh oh if people are comfortable with the definition of order, let us start doing some basic lemmas and get comfortable with the notation because yes, and then take some examples also. So our first lemma of the class, which is if p is a prime, oopsie, and p doesn't divide a, and a to the power n is congruent to 1 mod p, then d divides n. And I want you all to at least think and try this. Like, yeah, I want you all to try to prove this. Yes, it is. It's easy by Euclid's division lemma. So let's.
We can write n as dk plus r and
Yes.
say r is less.
Yes. Yeah, that's it. Sure. So we write, so let n be dk plus r, where r is less than d and k is an integer. Oh no, this doesn't look nice. Okay, why? Okay. So then we know that if n is 1 mod p and a to the power d is 1 mod p, implies a to the power r is 1 mod p. But r is less than d, which contradicts which, and if r is like a positive integer, then it contradicts the definition of the order, because we are essentially working with the smallest positive integer. So that implies that r is 0, which implies d divides n. Okay, great. So note that this lemma also gives you that d such order is unique, right? Okay, great. So now we can start working on problems. So problem 1. Show that n divides phi of a to the power n minus 1 for n greater than 2, a greater than 2. Your first problem.
Excuse me, can I please clarify something that about the Euler torsion function?
Yes.
So basically, phi of x is the number of coprime. I don't remember actually the number of coprime numbers of
Oh,
x. I remember.
okay. Uh, so okay. So for any positive integer, we define phi of n to be the number of oops, wait, oopsie, of positive integer less than, okay, we define phi of 1 to be 1. So less than or equal to such, okay, we call them m, such that m and then GCD are 1. So essentially, it's the number of positive integers less than or equal to the number such that it's relatively prime to it or co-prime. Is that fine?
Yeah.
Great. I actually forgot. Pranav told me that you guys are not familiar with this theorem. We can actually quickly prove this right now. Actually, let's prove it after I'm done with the material of the class. It's the idea of the proof is not used anywhere in the class, so I think it would be fine. Okay. So did anyone
Can you just explain the problem? I didn't understand.
okay. So show that so we have n is a positive integer greater than 2 and a is a positive integer greater than 2, and you need to show that n divides phi of a to the power n minus 1. Now you know that phi of a to the power n minus 1 is a number, right? It's a natural number. So this natural number will always be divisible by n. You have to show that. Phi of anything, phi of any number is a number because of the definition we have given. So show that number is divisible by n.
You mean like the number of numbers that's relatively prime to a n minus 1 is always divisible by n. That's what essentially we need to
Yes.
say.
Yes.
Okay.
Less than or equal to an minus 1 and relatively prime. So a to the power n minus 1. Yes. So I think we should look at the ideas we have gathered till now. Okay, I'll make a small idea box. Ideas we
I have some idea about the question.
okay, go on.
We can say that prime p such that p divides n,
Mm-hmm.
and say like a to the power phi n should be 1 mod p,
Mm-hmm.
and try to do something with that. I haven't quite sure about the second part, but
So you're taking a prime p which divides n.
By the way,
yes.
like one thing which I saw, like I had that idea, prime p dividing n. Also, one more thing is that we know that our order divides the number. So can we
Yeah.
show something like that n is the order of this?
Yes, we can. The prime p is a great idea, but I do not know a proof involving that idea, but it is quite used. So let me actually write it here so that everybody can see. Ideas usually involve using orders. One is we know that order divides n if a to the power n is 1 mod m. Like we know order divides it. We also will be coming across the prime ideas, like using prime, using minimus, the smallest prime dividing n, and so on. But currently, we'll use the first idea, and as one said, that let us try showing n is order of something, of something. But what are the objects given to us? The objects given to us or the numbers given to us are n, a to the power n minus 1. We know a is also given to us. And we know these are the numbers which are sort of given to us. So can we try to construct an order? Like, can we take two numbers such that n is the order of the number? Well, so let's see. We want,
N is the order of a mod a n minus 1.
yes. So firstly, I think first of all, you guys should note that a and a to the power n, the GCD is 1. Obviously, that is true. Next thing, in fact, is n is order of a to the power n minus 1 mod a. That is clear, right?
Like, how can we definitely say that? No, that's my question. Like,
Okay.
yeah.
So what is the definition of order? Order, so say order of a to the power n minus 1
Can
mod
we say the
a.
same argument when A is not a prime?
Yes,
Because we proved for a prime, I think.
so essentially here the lemma we used, nowhere we used the fact that it's a prime. We only used the fact that uh, the number p doesn't divide a. So everything is fine. I think I should have said
Okay.
you more clearly that we can define it. We can define order for any number provided the number, if the number is like, provided the number and the two numbers should have GCD1. That is the only condition you need. And you need that condition because then you can guarantee that there is an exponent such that you can guarantee that phi of m is the exponent such that it's 1 mod m. If they're not relatively prime, you won't get 1. Okay. I think I might have confused a bit. Yes. So if order of a to the power n minus 1 mod a is k and k is less than n, then you get that a. Oh wait, sorry, I wrote this wrong. My bad. Oops, oopsie, doopsie, oopsie, doopsie. My bad, my bad. I wrote this wrong. Nobody corrected me, which is sad, but okay, I should have corrected this myself. Then you get that a to the power n minus 1 divides a to the power k minus 1, and k is less than n, which is less than n. So that implies that k is 0. And we had a is greater than 2. So yeah. So the order of actually no, never mind. Order of a mod a to the power n minus 1. I still Rajul, I said that it holds for non-primes also. I said that beginning of the class, Mehi. I think. Yeah, I did. See, that's why it's actually star. Like I was working with modular prime, but it works non-modular prime too. Like modular and non-prime too. I think I did say that. Anyways, so we get that k is 0. So
Can you
currently,
explain this again, this proof?
yeah, sure. The proof is not done. So currently we found that n is the order of, so we wanted n to be order of something. And the somethings we got is a and a to the power n minus 1. So we claim that n is the order of a modulo a to the power n minus 1. Now, why is n order of a modulo a to the power n minus 1? Well, suppose not. Suppose order of a modulo a to the power n minus 1 was k and k is less than n. Then by definition of order, a to the power n minus 1 divides a to the power k minus 1. Right? Because a, because a to the power k is congruent to 1 mod
Yeah.
a to the power n minus 1. But k is less than n. So a to the power k minus 1 is less than a to the power n minus 1, which implies k to be 0. Because we are working with a strictly greater than 2.
Yeah.
I will still state this, the non-prime version also. because if so the non-prime version is if m comma a is 1 and a to the power n is 1 mod m, then that implies that order of a mod m divides n. Okay, good. I think, so currently we got that n is the order of a modulo a to the power n minus 1. Okay, but we know one more thing which divides, which is one possibility. So we know that a to the power by the Euler-Torsion theorem, we know that a to the power phi of a to the power n minus 1 is congruent to 1 mod this.
Yeah, and order divide this. So yeah, works.
Yeah, so we're done. And by the above lemma, we're done. So I hope everybody got this problem.
Oh yeah, we are done. Okay.
Okay,
Yeah.
great. Yeah, this is going to be very slow, but it's okay. I already said Pranav that I'll probably require two classes for this. Okay, our next problem is determine all n such that n divides 2 to the power n minus 1. And here we'll be using another idea, and here which doesn't quite involve. Okay, where is my ideas? Here. And that won't be involving the first idea itna. It will be involving a new idea called using primes. And like the trick here is
Smallest prime.
yes, smallest prime. Smallest prime will give you a lot of benefits. So I've already given a hint to the problem, which is considering the smallest prime. I hope you all try thoda sa and then we'll discuss it. ठीक है? The answer is 1. It is 1. But you forgot the solution? Yes. I wish I can actually do that in Enmo. Like in Enmo, they give like, those find the solution set, and it's easy to find the solution set, and then I wish I could just say. I can hear someone's mic is unmuted. Sanjana, can you handle that, please? Yeah, thanks.
Yeah, I was saying something. I couldn't hear you.
No, like somebody was speaking, so I said them to like unmute.
No, about Inmo.
Oh, about Inmo. No, I just said that I wish I could just write that I know the solution, but I forgot or something like that. But it's okay.
Yeah.
But it's fine. Like, yeah. I think we can use the expansion of. Ooh,
Can I say something about the problem?
yes, you can.
So as like your idea said, we can assume that P is the smallest prime that divides N.
Yes.
So like P divides N, so 2 to the power N minus 1 is 0 mod P.
Mm-hmm.
So 2 to the power N should be 1 mod P. So the
Mm-hmm.
order should divide N. And we know that by Fermat's-Littis theorem, it should divide P minus 1. So the order should divide P minus 1 also.
Yes.
And as the smallest prime of N is P,
Mm-hmm.
so P minus 1 and GCD of P minus 1 and N should be 1 or 2, I think.
Uh-huh.
And so D should be, I think, 1, I think. I have to
Huh.
work on this, but
Okay. Yes, it is. Can you see why n is odd?
yeah, N does not divide, like, if it 2 to the power N minus 1 is odd, so N should be odd.
Yeah, so your solution works, right?
Yeah, I think so.
Yes. So the proof he said is essentially the idea, and we will be using the trick I said. So the trick is to consider the smallest prime which divides n.
Sorry,
So,
one thing.
mm-hmm.
So what we know is that P divides like suppose P is the smallest prime that divides n, then we know
Mm-hmm.
that 2 to the n is congruent to 1 mod P, right?
Yes.
So that means P minus 1 divides n.
Uh,
And we also know that P divides n. How is that
but it
possible? Because, no, is it possible? Oh yeah, I'm
oh,
sorry.
you get the contradiction there itself, right? Okay,
Oh,
so we consider. So okay, first thing first, let's write the solution we got. So n equals to 1 works, and we claim that no other solution works. So assume. Oh no, why is okay? Let's yeah. I think this should be better. So n now is greater than 1. We will now consider the we now consider smallest prime p which divides n. Uh, n is odd clearly because n divides 2 to the power n minus 1, which is odd. So n is odd. We essentially,
right.
yeah,
I see where the contradiction comes. Right.
yeah. So we know that um, order of 2 mod p divides n as p divides 2 to the power n minus 1. By the lemma, we have that. But we also know that p to the power, p divides 2 to the power p minus 1 minus 1. And that implies, so this implies order of 2 mod p divides p minus 1. So that implies order of 2 modulo p divides the GCD of n and p minus 1.
That's
I
one.
mean,
That's
yes,
one.
which is 1. It can be
Can
2 also, but we had that n is odd. Actually, yeah, never mind. It can't be 2 also. Anyways, Yeah.
Can you please tell how?
If we take 2 also, we can do like 2 squared is 1 more p. So 3 is 0 mod p. So p should be 3. And we can get contradiction in there also.
Mm-hmm. Okay. Someone had a doubt.
Yeah,
Yes.
I'm actually confused how p divides 2 raised per n minus
Array, because n divides 2 to the power n minus 1, no? And p divides n.
1. Oh, okay. Okay.
Yeah. Yeah. So I just had one thing. Like I think that this is all this can be avoided. Like, can I just write something? If you allow.
On the board, do I
Yeah.
not
Yeah.
allow?
Yeah.
Do I, you can write on the board, right?
Yeah. Yeah. Okay. Just say. So can you see, right?
Yes, I can.
Yeah. So we know this happens. This is 1 mod p.
Yes.
So also what we know is that p divides n.
Mm-hmm.
Then also as this works, therefore we also know that p minus 1 divides n.
How do we
But we
know
know,
p divides n? Oh, yeah,
yeah,
sorry,
we
we
know,
know p divides n.
yeah, so we know this, but n was odd and p minus 1 is even. So the
Yes,
no prime divides, therefore n is 1. This
yes.
should be like, can we just do this? We can just avoid the orders.
Um, you know p divides n? Yes. How do you know p minus 1 divides n?
Yeah, but this two, the p minus 1 cannot divide n because n is even, because it's odd. N is
No, but
odd
how do you know p minus 1 divides n?
because this happens, and also we know that 2 to the p minus 1 is
Yeah,
common to 1.
but p minus 1 is not the order.
Ah, right.
Yeah.
Okay, yeah, got it, got it.
So you
Makes
need
sense.
to essentially use the idea of orders here. And luckily n and p minus 1 have GCD1. So this is like way more stronger. Anyone else who has like a doubt?
I'm still confused in the second line, like 2 raised
Oh,
per p
okay.
minus.
Yeah, so you know that 2 raised to the power p minus 1, uh, p divides that number because of
Yeah,
Fermat's little theorem.
yeah,
And so by definition, order of 2 mod p divides n, and then order of uh, 2 mod p divides p minus 1 because we have these two satisfying. And
okay,
so
yeah,
order of 2 mod p divides the GCD of n and p minus 1, which is 1. It has to be 1.
yeah, because
So
p divides n.
yes, p divides n, and also p is like the smallest prime. So
Sorry.
n equals to 1. Has to be 1. Here we also use the fact that p is the smallest prime because n and p minus 1 will have GCD 1. P wouldn't
Like,
have been the smallest prime, then this wouldn't be.
can't just P be any prime that divides n because it works for all primes.
How about this? Uh, how about this? Consider n to be something like 5 into 4, I guess. And the prime is 5. Then what was I doing? Yeah. So like GCD of n and p minus 1 is not 1 here. Right? Disturbance. Can you do something? Thanks. Yeah. So n is 5 into 4 and p is 5. It's not the smallest prime dividing n. And here GCD of n comma p minus 1 is not 1. P minus 1 here is 4. So yeah, here you
What
need
was the
to.
contradiction used?
Okay, so here I considered the smallest prime p which divides n. So GCD of n and p minus 1 has to be 1, because if GCD of n and p minus 1 is greater than 1, then that implies there exists a prime p dash which divides n and p dash which divides p minus 1, which implies p dash to be less than p minus 1. But I assume that less than or equal to, but I assume that p is the smallest prime, so there cannot be such possibility. Now, the other kid asked me what's the need of the prime to be the smallest. I need the prime to be the smallest in order to guarantee the condition that the GCD is 1.
Got it.
If
Got it.
p, yeah, if p is not the smallest, then it might not be 1. For example, consider this example, where n is 5 into 4 and the prime is 5. Then GCD of n and p minus 1 is not 1. So yeah,
Now the order must be 1.
yes, the order must be 1. So p divides 2 to the power 1 minus 1, which is 1. So n is 1. Yeah, so we're done with this question. Good job, everyone. Let's move to the next question. Is everybody clear with the above question? Yes,
Just
no.
a second. Let me. Can you just show the solution? Let me see. Okay, so here we get an order of p. Here you considered order of p with order of 2 modulo p, right?
Mm-hmm.
That's n. That divides n, correct. That divides p minus 1, 2. That divides. So order of 2 p is 1. Yeah. Just I Acha, okay, so p is 1. P is the smallest prime is 1. Makes sense.
Yes. Okay, great, great, great. The next thing we have is, it is also sort of the same idea, but we shall still do it. Prove that my handwriting progressively became bad, but it's okay. That is life and health. Prime factor. Prove that any prime factor. Yeah, I'll go with prime factor of 2 to the power 2 to the power n plus 1. Like the plus 1 is alag se, it's not in the plus 1 is congruent to 1 modulo 2 to the power n plus 1. So the question says that prove that any prime factor of 2 to the power 2 to the power n plus 1 is congruent to 1 modulo 2 to the power n plus 1. Yeah, this looks a bit intimidating, but
Just a question. So here we have that any prime factor of 2 to the 2 to the n plus 1 is congruent to 1 modulo 2 to the n plus 1, right? What if the prime is small? What if the prime is smaller than 2 to the n plus 1? Therefore, the prime can be 1 only, which is not possible. So, okay, yeah, are you implying that every prime factor of 2 to the 2 to the n plus 1 is greater than 2 to the n plus 1? That's not the case. According.
yeah, any prime factor, any prime number which divides the number I
Wait, what happened?
Oh, I have no idea why I left that meet, but it's okay. Did that go for everyone? Or like
Yeah.
No, you were
it,
the only one.
I was the only one who went?
Yeah.
Hey, this is so mean. Why so
I was
mean
telling
of them?
I was telling the truth. I'm not being mean.
Honey, it's okay. You're not mean. Like I said mean to the Zoom
Oh,
person.
yeah, they are.
Yeah, bad people. Only Samira. So I have to write the question again.
Like,
Oh
did everything
no.
just go off?
Yes, it did. That was so nice. I could have downloaded it. I could have sent it in the group, but it's okay. It's okay. We'll do it again. We shall do it again. So the problem says that prove that any prime factor of 2 to the power 2 to the power m plus 1 is 1 modulo 2 to the power n plus 1. Yeah.
Isn't 2 to the power 2 to the power n plus 1 a Fermat number?
It is. The maths
Oh.
number isn't it like supposed to be a prime though? Or I do not have that much knowledge though. Let me actually just search it up. Format number.
All format numbers are not prime though, so yeah, it makes sense.
Yeah, okay. Formats number are of the form 2 to the power 2 to the power n plus 1. Yes.
Yeah. And there are format primes, but all format numbers are not prime. To
Yes.
answer that question. Yeah, like, but
In
my
fact,
question,
go on.
my question still stands though. Like, is this implying that every prime number that divides 2 to the 2 to the n plus 1 is greater than 2 to the n plus 1?
Yes.
Okay, that's an interesting thing though.
It is. It is very interesting. You guys should come to Promise India if you like this question.
I applied, but I was rejected though. High and
Oh
lowest.
no. I went to Promise India as a student in 2023, and I was a counselor this year. So, yeah, it's pretty fun. You guys will like it.
I wrote like a 50-page PDF, but still got rejected.
Yeah, exactly. We both were rejected.
Oh no.
Same here.
I wrote a 53-page PDF. They accepted me, which is weird. They don't accept Olympiad students now. But it's okay. They'll accept next year. Just like show you like a small tip for anyone applying for Promise. Like, don't do just the problem. Like, do more than the problem asks you to do. Like, be a mathematician. Generalize the problem.
I
Write
mean,
comments.
sometimes we're not even able to solve those problems which are asked. Like, these year's problems were like so much crazy, more crazier.
Oh.
Yeah, there was like a problem which I forgot, but that problem was crazy. I used code to solve that problem though, but still the problem was not solved.
Hmm.
I even tried
You
to
could write
visualize
it
the
up.
graphs.
Oh. I think one thing is they do not usually like if you use any calculator graph or anything. Just like use your bare hand. Also, like it is pretty hard to get teachers' recommendation actually. Um, I'm not sure, but like I know some people who applied to Promise, like India, like the Olympiad community, say they got waitlisted and they used like they had Rohan's like a CMI student's recommendation letter, and they don't mind it, I guess. So even if your teacher doesn't do it, like if there is a Olympiad instructor, like with whom, which who you like who guided you, then they can write a recommendation letter also.
Yeah, I
They
didn't find it.
understand that.
I didn't find a problem writing the recommendation letter. Like all my even my form was filled. The thing was the problems. Like
I
you said,
think like next time just like generalize the problem or like try small cases and like for each problem write 10 pages. Like get I if you can't solve it, like you would
what do you
love
mean
that.
10 pages? What?
Like 10 pages are like we'll talk in DM. It's essentially you want to show them that you can try the problem in a lot of directions and have a lot of ideas. Like be a real mathematician. Anyways, any idea for this
Yeah,
problem?
yeah. So just
Yes,
write,
I have some idea.
Go
just write
on.
p divides that thing, and when you do it, actually you will find that 2 to the 2 to the n is converted to minus 1 mod p. Square it, then you will get that 2 to the n plus 1 is 1 mod p, right? And
Mhm.
and you will see that you get the power there, and that you can associate it with orders, I guess.
Ha. Anyone
Yeah. So
else who also had idea? Like someone else was also speaking.
Yes, I have an idea. Like I did the same thing and got like order of 2 to the order should divide like 2 to the power n plus 1, but shouldn't divide like 2 to the power n. So the order is 2 to the power n plus 1. And
Yes.
now just use Fermat's little theorem and to get the result.
Yes. So say p divides 2 to the n plus 1 and p is a prime. Essentially, it doesn't matter though, but okay, it does. P is a prime. Then, firstly, note that 2 to the power 2 to the power n is congruent to minus 1 mod p. That implies that 2
that
to
you
the power,
square it,
yeah, you
n plus
square
1
it,
is
you
converted to
get
1
that
mod.
it's 1 mod p.
Yes.
So, what does it give about the orders?
It gives that the order of this number divides 2 to the n plus 1. And yeah,
Divides 2 to the power n plus 1.
correct. And
And
so it
we
divides
know,
2 to the p minus 1.
yeah, and we know that the order does not divide 2 to the power n because it's minus 1 for that number. So that
Right.
implies that order of 2 mod p is 2 to the power n plus 1.
Can we do that?
Yeah.
Oh, damn. That's a nice idea though.
It is. It's a pretty nice
Wait,
idea actually.
I couldn't get the nice idea. How did you get that it doesn't divide 2 raised per n?
Because if it would divide 2 raised to the power n, then 2 to the power 2 to the power n would have been congruent to 1 mod p.
Okay,
है
yeah.
ना? I think I did not mention it अच्छे से, but like if I have, so if order of A mod M is D, then we know that A to the power D is congruent to 1 mod M. And that implies that if any multiple of D, say Dn, would also be 1 mod M. So A to the power D, which is 1 mod M. So yeah. So if order of P, order of 2 mod P would have been dividing 2 to the power n, then you would have got a 1 mod P here. So yes. So order of 2 mod P is exactly 2 to the, is exactly 2 to the power n plus 1.
So this means that p minus 1 divides 2 to the n minus n plus 1, and that's done.
Almost. Somebody was saying though.
Couldn't it be something smaller? How are we sure that it is the
I mean,
it
like
is the
what are okay? So if a number d divides 2 to the power k, then what is what what is the what what is the prime factorization of d? Like the only like
two
d will
powers?
also be of the form 2 to the power k dash, and we know that this number order of 2 mod p does not divide 2 to the power n. So it has to be 2 to the power n plus 1 now. Because
Okay, yeah, okay.
Yeah.
Got it.
yeah.
Yeah,
So
got it. You Fermat's little theorem.
so order of 2 mod p is 2 to the power n plus 1. But we also know that p divides 2 to the power p minus 1 plus 1. So the order would divide it. So the order, which is 2 to the power n plus 1, divides p minus 1, which implies p is congruent to 1 mod 2 to the power n plus 1. And we are done.
We use the same kind of idea for Farmer's Christmas theorem, I think.
Oh, yes. You guys have done Fermat's Christmas?
No, not here in the class, but otherwise.
Yeah. So we'll be doing Fermat's Christmas theorem in here also. Hopefully. We have time to do that. Yes.
Can you please tell what was the intuition for this problem?
For this
Like,
problem,
yeah, for me it's
if
hard to follow like that, but
अच्छा ठीक है. So essentially the intuition comes it it comes along this thing we used here. Let me use some other color. Oh my god, there's a pink. Oh, that's poop. Oh wow, so pretty colors. Okay, so sorry. So essentially this thing, is this too light? Can you guys see it? Okay, this is probably too light. Like essentially here, that is the main idea. Because I knew this was an order problem. So I need to use the order somehow. So when I used the order, I got this whole thing, which then essentially gives me this. But I still need to show that P is congruent. I need to show that P is congruent to 1 mod 2 to the power n plus 1. So if I backtrack it, I need to show that 2 to the power n plus 1 divides P minus 1. And essentially, how did we proceed the first problem is not there. How did we proceed the first problem? Remember the first thing. So it would have
order.
been, yeah. So essentially, it would be nice. It would be nice if 2 to the power n plus 1 is order of something. Right. And it turned out to be order of 2 mod p, which we showed, and yeah. So I think the main intuition is the division condition of like p being 1 mod 2 to the power n plus 1 gives us an idea of like maybe we should try order, and maybe we should try showing that 2 to the power n plus 1 is order of some two things. and then it was manipulation. So I think that's the intuition behind it.
Yeah, actually, when we did this backtrack thing, I was able to think that maybe we need to take mod p somewhere. Otherwise, I was stuck on the first statement itself.
Mm-hmm. Okay. Okay. So now I think we can go to something new, which is called primitive roots. And oh, yeah, sorry. Um, primitive roots. Is my handwriting like too small? Should I like write big?
Nah, it's feasible.
No,
Okay, good.
it's fine.
Okay. So primitive roots. What is primitive roots? Actually, before going to there, um, let me motivate what primitive roots are and like why we should care about such numbers. Well, so remember the case like 4 to the power 12 is 1 mod 13 and 4 to the power 6 is 1 mod 13. So 12 is not the order of 4 modulo 13, which okay it does give like yeah fine d is smaller than p minus 1, but like what my next question should be like, are there numbers whose orders are phi of m itself? What I mean is, if I have a and m to be 1, like GCD of a and m to be 1, we know that, and then let d be the order of a modulo m. My question is, does there is d equal to phi of m? Or better question is when, for if we fix if we fix the m, does there exist an a b is equal to phi of m? Now why do we care about this question? We care a lot about this question because we know what phi of m is, right? Like we know the formula for phi of m. For like we know that phi of p is p minus 1 for prime, and like the general formula for phi, which is like if nah, I won't like that. But point is key. I know what phi of m is, so I have more properties about the orders, and which would additionally help me in developing and more on the structure. Yeah. So question is, can we find an A? Answer is for some M you can. So yeah. Uh, so what are primitive roots? This motivates us to define primitive roots. What are primitive roots? Given a positive integer n, if order of g modulo n is phi of n, where G and N has GCD1, then G is called a primitive root. Modular N. Or primitive root of N. Yeah, the definition. Did everyone get the definition? Essentially, the order is phi of N.
Yeah. Okay, got it.
Got it. Great. So, first question.
And you just repeat once.
Oh, okay. So, the definition of primitive root is if you have a positive integer n, and you have g comma n is 1, and if order of g modulo n is phi of n, then g is called the primitive root of n.
And show an example, it's too much confusing.
Sorry?
It's a little confusing. Can you show an example?
Yeah, sure. So, let us work with n equal to 3. We'll go with higher examples also. Let's first work with small numbers. You have n equal to 3. So is
G4
one
works. G4.
G4. So let's work. Is 1 a primitive root?
Yep.
Yeah.
Um.
2 also.
Well, how is mm, how is 1 a primitive root?
1
I know
square.
that.
1 square is 1 mod 3.
But I said the order must be 2. But 1 to the power 1 is also 1 mod 3, no?
Oh, okay. Makes sense.
The order. So no, 1 is not a primitive root. No, 1 is not.
2
If
is it.
2 is, yeah, 2 is a primitive root. How do we check that 2 is a primitive root? We, yeah, like 2 to the power 1 is congruent to 1, is 2 mod 3. And 2 to the power 2 is congruent to 1 mod 3. So it is a primitive root.
Is there anything like p minus 1 raised by p minus 1 is the p minus 1 is the primitive root of p? Anything sort of that?
You know, I mean, you'll get that, Abhi. Let's work with n equal to 5, which is your prime. Is 1 a primitive root? 1 cannot be a primitive root.
1
No,
is never
never.
a primitive root.
Yeah, never.
Huh.
Or n equals 1.
So we got that 1 is never a primitive root. What about 2?
It is.
Okay, let's check.
Oh no, I didn't check. I didn't check properly.
So 2 to the power 1 is 2 mod 5. What about 2 square?
Minus 1 mod 5.
Minus 1 mod 5. 2 to the power 3.
3 mod 5. Since it is a prime, it is.
3 mod 5. Yes, correct. And 2 to the power 4 is 1 mod 5. So it is. So it is a primitive root. Because because 4 is the order and 4 is 5 minus 1, which is 5 of p. So 2 is primitive root. What about 3? Do you guys think 3 is a primitive root? Anyone?
It is a primitive root.
Yeah, it's a
Yeah,
primitive.
it is a primitive root. 3 cube is 27, 2 mod 5.
I mean, 3 square is minus 1 for mod 5. So the
Yeah.
least number will be its square. That's pretty.
Huh. So 3 is also a primitive root. So what about 4?
4, 4, 6.
It,
Yeah, no,
it,
it's not 4 square. Works.
It
4
isn't.
square. Yeah, 4 square is 1 mod 5.
It's sad.
It's sad. So what did we get?
We
First,
got that all primes are primitive roots.
Yeah, something like that.
yes, we did not get that, but that's a conjecture. So I will not be proving this conjecture. There's like it's something which is there in any number theory textbook, and the
What's the
proof is pretty
conjecture
long.
that any prime is a primitive
Is
root
it
root
not
of
yet
another prime?
solved?
The conjecture you guys got is any prime will have a primitive root. I guess that's
No, no. The conjecture I was thinking that yeah, that's one conjecture that any one prime will have a primitive root. The
hmm.
another conjecture is that all the primitive roots of a prime will be a prime. I guess that's wrong though.
That is definitely wrong.
Are you sure? Can you give a counter example?
I know, I know there are numbers which do not have 2 as their primitive root. I can't come up with right now. Maybe 13 or 17 will not have 2 as their primitive root.
We can take
7
n
won't have
as
it
7
as the
and
primitive root.
2 cube.
Huh?
Is the first conjecture proved?
2 is
The
not the primitive root of 7.
Yeah, 2 is not the primitive root of 7.
I mean,
Okay.
can you find a composite primitive root of 7?
Yeah,
Yeah.
I'm pretty sure. Um, 7. What's 7's primitive root? 3, right?
Yeah,
Or
3.
is 2 like a primitive root of 7? Like we know 2, and then we know 2 square is 4, 2 cube. Okay, great. Yeah, it's not. Um, yeah, there is. Point is, the second conjecture which you guys made, someone made, is n has the primitive root if and only if n is equal to 1, 2, 4, or is of the form p to the power k, or 2 into p to the power k, where p is odd prime. That is the big theorem.
Wait. Just a second. Uh, n is 1. Are you sure? Because 1 to the anything is 0. Mod 1.
Well,
Is the
point
statement
is,
true?
huh?
Is the statement true which you wrote now,
Yes, it
or
is
a con? Oh,
positive
okay, it is.
integer.
Yeah, p raised per k doesn't contain 2.
Yeah, doesn't contain 2. Like 2 is alag. P is an odd prime.
Okay.
Yeah, so this is like the big theorem thing, which I won't be proving. And rather will be essentially proving some lemmas regarding primitive roots, involving primitive roots. ठीक है?
Then all the other numbers will not have primitive roots.
Yes. it's a very good exercise. You can try it on your own. I think first thing first, which you should try is proving that powers of 2 will not have a primitive root uh, bigger than 2 to the power 2, like bigger than 4. Like 8 doesn't have a primitive root. Think why. It's a pretty nice problem. You guys should do it on your own. Another lemma, and I think uske baad we'll end the class. ठीक है? Also, like, I will definitely be taking a part of this class, so it's okay. Given a prime P, and since it's a prime, we know it has a primitive root. So its primitive root is G. The set G to the power 1, G squared, G to the power P minus 1. It forms a complete set of residues modulo P. Which means that G to the power 1 up to G to the power P minus 1 to up to P minus 1 in some order. Did everyone get what the statement
Yeah,
means?
got it.
Yeah. So we can actually see the example here. For example, when I considered n equal to 5, I know that 2 is a primitive root. And when I considered 2 to the power 1, 2 squared, 2 cube, and 2 4, the set I got was equal to, 2, 4, 3, and 1, mod 5, which is the complete residue modulo 5. Similarly for 3, we got that 3 is a primitive root. And we got all the set of residues. So yeah.
I completed the proof for like if n is 2 power if n is 2 power k where k is greater than 2, then it won't have a primitive root.
Oh, would you like to share the proof?
Yeah, so basically the number is it's either 0 or 1 minus 1, like we can take it mod of 2. So basically if n is greater than 2, that means that at least phi of n would at least be 4. So but every number would be having like any number to power 2 would be one mod that number, like something like that I tried to prove.
I didn't quite get your idea. So actually, you know what? You can like DM me Discord man. I can check your proof. Does that work?
Okay.
Okay, cool. Okay, so the people here, do you guys have any ideas on how to do this?
I have read a similar kind of problem while I was reading residue class, but I'm trying to do something similar.
Okay. Would you like to share the idea then? Oh, okay.
Actually, it
Okay.
was showing a set is showing that the residue set is equal to this set, something like that. Taking mod, like showing that it has equal number of elements and no elements are co-prime, something like that.
Oh. Mm-hmm.
Is this a question? We need to prove this question.
Yes, you need to.
Wait, I was not. I didn't done. 1 second. So we have to prove that this set forms a complete set of residues modulo P. Okay.
I was explaining, I was giving the example here.
Yeah. Can you hear me?
Yes, I can.
Yeah, one thing we can do is that if it is not a complete set of residues modular P, this implies that there are two numbers in this set that have equal residues mod P. We can just equate them and bring a contradiction. That's
Yes. Yeah, correct. That's the idea essentially. And it's a pretty you guys had a pigeonhole class, right?
Yeah, I have read similar proofs. G raised
Yeah,
per I is congruent to G raised per J mod.
yeah. So we can do like suppose not, then by pigeonhole principle by PHP there exist I and J such that G to the power I is congruent to G to the power J mod P, and I is strictly less than J, strictly less than P. Then what do we get? Then that implies that G to the power J minus 1 is congruent to 1 mod P. But we know that uh, we know G to the power I, G to the power J minus I is congruent to 1 mod P. And G minus I is strictly greater than 0 and strictly less than P minus 1, which is a contradiction. And this is not possible unless like J and I are equal, but then we assume that J and I are not equal, but then G is a primitive root, so contradiction. Did everyone get it?
Couldn't get how you got G raised per J minus I is 1 mod P.
Oh, I just didn't, am I not like, I think like G to the power J is congruent to G to the power I mod P. That implies that P divides G to the power J minus G to the power I, which implies that P divides G to the power I into G to the power J minus I minus 1. But then I know that G to the power I is congruent to but then I know that G to the power I and P has GCD 1. That implies that P divides G to the power J minus I minus
Yeah, I
1.
couldn't get how their GCD is 1.
Because G is like a primitive root, right? So G to the power P minus 1 is 1 mod P. That would imply that G and P is 1, GCD 1. So G to the power I and P are GCD 1. Does that make sense?
Oh, okay. But okay, got it.
Okay, yeah. So P divides G to the power J minus I minus 1. So yeah. Did everyone get the proof? Yes, no, yes, no, no, yes. I assume
yes.
yes. Great. Okay, so let us just prove Wilson's theorem and I'll end the class with Skipat. Like one direction of Wilson's theorem, which says
If P is a prime, then P minus 1 factorial is 1.
yes,
Plus 1 is 0 mod. Is that the
yeah,
one direction? Another direction, I guess, if that happens, then P is a prime. That is that provable by element.
it is provable by elementary stuff. You guys can do it, I'm pretty sure. So the statement we will be proving is given P is a prime, then P minus 1 is congruent to minus 1 mod P. Now, there exists a general proof which is essentially like pairing the numbers
Yeah, read the
pairwise
diagram.
and yeah, but this is a different proof and we'll be using the idea of primitive roots. We know that P is a prime. We know that P is a prime. So we know that it has a primitive root. There exists G such that G is a primitive root of P. So उसके बाद क्या करें? What should we do next? We want to show that P minus 1 factorial is congruent to minus 1 mod P.
Yeah, we can just write them in the form g square, g cube, and so on till g to the p minus 1. Then like multiply everything. We'll just get g raised to the power p minus 1 times p by 2. So like g raised to the power p is just g. So we just have g raised to the power p minus 1 by 2, which is just minus.
It's the proof. I will let everyone now think अच्छे से because like they already said the proof, but like you guys should.
I mean,
Right.
like without using primitive roots, we can do it, right? It is
Yes,
easier.
we can. That proof is pretty well known, I think. Like
Multi-thread, I guess. Like yeah,
yeah.
you just consider p minus 1 multiples of p and multiply them all, and you just get p minus 1 factorial, and the
Mhm.
p stuff cancels, and you get yeah.
Yeah. So let us try to prove this. So as they suggested, we know that p minus 1 essentially like p minus 1, p minus into p minus 2, the 1. But then these are just the residues of p, and we know that by the above lemma, g to the power 1, g to the power 2, up to g to the power p minus 1, this set forms a complete set of residues modulo p. So this is essentially in some order same as g to the power 1 into up to g to the power p minus 1 in some order, which is essentially g to the power p into p minus 1 by 2, which it is essentially okay. Let us now think p. Now, what is g to the power p minus 1 by 2 mod p? We are working mod p, so let's just write mod p. What is g to the power p minus 1 by 2 mod p? Can it be 1? No. So it has to be minus 1. So this is minus 1 to the power p mod p.
Why 1 and minus
Okay.
1?
Yes. So clearly g to the power p minus 1. Oh my god. Can you guys hear the train? G to the power p
Trains
minus
are
1.
nice, very nice. Bro.
So g to the power p minus 1 by 2. It cannot be congruent to 1 mod p because p is a primitive root. Okay, essentially, let us first deal with this. I have x square congruent to 1 mod p. That implies that x minus 1 into x plus 1 is congruent to 1 mod p, which implies x is either
That should
1 mod p.
0 mod p.
Sorry,
That should be a 0 mod p.
what should be 0 mod p?
Second step.
This implies that x square minus 1 is congruent to 0 mod p. Oh, sorry. Oh, this. Oh, my bad. Thank you. Thank you. Yeah. So that implies that x minus 1 into x plus 1 is 0 mod p, which implies that p divides x plus 1. If p divides x minus 1, then x is congruent to 1 mod p. If p divides x plus 1, then x is congruent to minus 1 mod p. Here, Rx is equal to g to the power p minus 1 by 2.
And x square is 1 mod p.
Yes, and x squared is 1 mod p. Now, x cannot be 1 mod p because g is a primitive root. So that implies that x is minus 1 mod p. So yeah, so g to the power p minus 1 by 2 is congruent to minus 1 mod p. Not p factorial, that was just an explanation. So yeah, so we're done.
Can you show the left hand side downside of it for once?
This thing,
Yeah.
anyone has a doubt? Any doubt, anyone? No doubt. Okay, so I'll stop here. We have covered essentially everything theoretical and some basic problems. In the next class, I take we'll be doing some more lemmas and we'll be doing some more problems, some actual problems related to orders and primitive roots.
Here,
Uh,
why x cannot be 1 mod p? Still confused.
X cannot be 1 mod p because of how we define primitive root. G is a primitive root mod p. Oh, G is a primitive root mod p.
Okay, p minus 1 by 2 is smaller than p minus 1.
Yeah,
That's why. Okay.
yeah. I should have been more clear. Any other doubt? Should I stop presenting? I'll cancel this thing then. Okay, I'll stop presenting. No doubts, right?
No.
Okay. How do I stop presenting? Oh, okay. Stop share. Great.
You're done, right? Should I stop recording?
Yeah, I'm done. You.